Alright, I thought I would cover this little, you know, HX711, 24-bit analog to digital converter. It's usually used for load cells. Because, there's something that always puzzled me about this, and I'm also going to cover the idea of using this as a general purpose voltage meter, too, by the way. So, later in the video, it might be a kind of long video. I don't know. We'll see. But one thing that's always confused me about this as a load cell, was okay, why the fuck are they suggesting this arrangement? It seems to me that a quarter bridge arrangement would be the more logical thing to do. That's where you have, basically three fixed reference resistors, and then, one of the strain gauges is a variable resistor. Well, as it turns out, you can do it that way, and we'll get into that in a minute. But they suggest, actually having all four of these load cells, connected in a full bridge. And I was like, why the fuck would you want to do that? I mean, it just always confused me because, what the hell are they doing? I mean, it's like I said, okay, let's say you get this into a balanced position with no load on it, and here's one of your outputs, and here's another one of your outputs, right? Um, and so that's where you're taking your measurement across the bridge, right? Like you should. Um, well, the thing is, okay, the thing's balanced. Let's say you got it tweaked or something, and it comes out to 0 volts, which is unlikely, but let's just say you got lucky and all your sensors were perfectly balanced to 24-bit resolution. So you get 0 volts across the bridge. Well, the thing is, if you were to equally load all these four sensors, wouldn't that still generate 0 volts across the bridge? The only time you get a non-zero volt reading is if one of them was out of balance with the other. One of them had a slightly different load, and that doesn't tell you anything, because then you're just getting a measurement of how out of balance your bridge is, all right, but you're not getting the weight. You're just getting how out of whack it is, and you don't even know which sensor's out of whack. So I was like, it just doesn't make sense, and I was just pulling my hair out about it for a long time until so I did some research, because that's confused me for a lot of years. That what are these stupid idiots thinking? Because that's exactly what they recommend. Just like this. They recommend all these sensors get hooked up, kind of like that. And I happen to have a scale that has some of these very same sensors in it, and yep, they sure as hell use all of them. So it's not like they're using one of these, all three of them as some kind of a thermal sensor or something. Like, for example, used it in a half bridge, yeah, you could have a dummy load, I mean, as a quarter bridge, you could use one as a dummy load just to give you, like up here that you don't apply any weight to, just to give you a thermal balance, because these things tend to be very temperature sensitive, particularly at 24-bit. So that would make sense, if you had like one here that you didn't apply a load to, but it's just to give you a temperature stable reference with this one. It's the exact same sensor. Okay, that would make sense, and this is the one you apply the load to. Okay, then you can get a reading, with these two being fixed resistors. But, you don't see anybody talking about that on YouTube videos or anything else. I mean, Great Scott, I think, talks about, using it that way, but he doesn't go into detail about the whole concept of thermal imbalance and everything, which is a big problem, on these. Oh, maybe he did talk about that a little bit, but that he didn't really explain, this whole concept. He mentioned that you could do it, as a four-way bridge, but he didn't really explain the theory of what the hell you would do that for. Because I wouldn't even understand in a half bridge to use it until, so I went and did some research on it, and it makes perfect sense. Duh. I found this article here, which I might put a link to in the description. I don't know, but you can kind of Google it yourself. But it's by National Instruments, and if you go back here, here's how I found it. By Googling this, and then it was this place here that brought up that PDF. But yeah, I mean, they actually go through and explain that, well, how it works is that, And here's how you'd work with a dummy gauge right here, like I was talking about, that one of them you wouldn't apply force to and the other one you would, because you could just have one just sitting around with no force applied to it at all. um, and that's a dummy gauge, so you can use this for thermal balancing, because again, the temperature, like they explained in this article, changes a heck of a lot. So the fact of the matter is, you can use it that way, but you can use it in a half bridge, like they show here. But this is how you do it. You use one that's in tension, and the other, is basically in compression. So, like they talk about here, so that actually amplifies the sensitivity of it if you do it that way. But you got to do it, kind of in a way like this. And if you go four bridge, just like they show here, well, you could put four of them, with two of the opposite corner, legs being, in compression, and two of the other opposites, being in tension. So, and that multiplies your, your sensitivity again. So it's a way of way increasing your sensitivity. But they don't explain that. Those modules look like they're all the same, and for all I know, they might be. I really don't know. That if you're supposed to put some of these upside down or whatever. But I mean, the fact of the matter is that that it's the same concept. So. Now, of course, in a scale, it does occur to me that, they're probably not going to be equally loaded, but then again, these may be half-bridge elements. I don't know whether there's 3 wires coming out of them. So I would have to see what they do, but that makes me suspect this is actually 2 strain gauges, one on top of each other. So if they're using it like that, it still sort of doesn't make sense, because then you're back to, you don't have this configuration if all the strain gauges were indeed a half bridge. You wouldn't want to use 4 of them. You just want to use 2 of them. Because in theory, okay, this is 1 wire, this is 1 wire, and this is 1 wire, right? And if you look at how they're, doing this here, the wiring, configuration is a little confusing. I mean, I do not know what the schematics on this actually look like inside. Let's see, input power, yeah, I don't, see, white, red, and black, okay, that doesn't really tell me much. W1 to W4, but anyway, yeah, I'm still not really sure what the theory of this is yet, because I actually haven't played with one of these. But again, I do have a scale that just does have these exact same sensors in it that I guess I got at a thrift store or something that didn't work, but or didn't work properly. But I assume they're doing something like this, and I assume that it works. Despite I've never tried it, but I assume that it works just because I've got a scale that has this exact arrangement in it. So it must work. I just don't know what they're doing inside these sensors yet. So I'm just going to take their word for it that this works with their sensors. But at any rate, but this is the actual theory, of how you use this, and that's how they make this work, is by putting in an opposition like this. So, if you didn't do this exact arrangement they have here, well, you might, again, if you had equal weights on all 4 sensors, you'd still have 0, because, let's say both halves of this bridge were this way, the top in compression and the bottom in tension, you would end up still with 0 if everything were perfectly balanced, and then you just end up with a, again, an indication of how out of whack your sensor is. I guess you could figure out which side is sort of out of balance if you did it that way, because it would either be a positive voltage or a negative voltage, but you still don't know if these 2 sensors are in balance. At any rate, this is still how to, how to basically use the thing and what the actual sensible theory behind it is. Again, I'm still not really sure what the internal makeup of these sensors is, but more research would have to be done. But again, I assume that it works. So, but at any rate, it certainly occurred to me, like it has some other people, that since this is a, this particular sensor, which is an HX711, there's actually a 24-bit ADC in it. Could you use it as a voltmeter? But if you look up the data sheet, it turns out that you could do it in. Let me see. Yeah, because I mean, you got some, some articles on some of these Arduino websites about some people that were trying to do just that. Um, and it certainly can be done. Let's see. The other one is just to show you, so you can look it up yourself, just by Googling these titles. But, there was some interesting information, mostly a bunch of bullshit, people blowing smoke at their ass. But the fact of the matter is that, it is doable. You can use it. And if you look up the data sheet of the, let me see if I didn't really want to do this, but, I didn't want to really talk about this that deep, but you can go to SparkFun and look at their data sheet. It tells you a lot of interesting things here, but one of the big things it tells you is that, they have this PGA amplifier in it. The problem is channel B, is limited to, channel A, you can select between gains of like 64 and 128, but that's it. And channel B, you're stuck with a gain of 32. What that means is that channel A, you can make as broadly sensitive as possible. So it could be either like 20 millivolts full range, or plus or minus 20 millivolts to plus or minus 40 millivolts if you go to 64 gain. The channel B can go down to, can go up to 80 millivolts full, plus or minus 80 millivolts full range. But that's still, 80 millivolts, that's still pretty tiny. That means you're going to have to use a lot of voltage division, and you're going to start really hitting your noise floor big time. If you can't measure over a larger voltage than that, it'd be nice if you can go the full 5 volts of the device, but you can't do that with this. But still, having said that, you could still use it as a voltmeter, but you got to remember these are differential inputs. So you don't want to just like tie one leg to the system ground. Okay, what you want to have is like an external circuit, that has like what you're measuring, a reference that you're measuring across, voltage divider basically, coupled with, some kind of input impedance to it, so that you get a nice voltage division to measure across that. In this case, would have to be no more than 80 millivolts if you want to, for full range. Otherwise, it'll just start clipping. That would be the end of it. You could apply more than 80 millivolts across it ostensibly, up to the power supply voltage, I'm sure, but you're not going to get any reading, above plus or minus 80 millivolts. And this is dual range, so given the fact it's a 24-bit, unit. See, here it's talking about the gain here, the noise level. But anyway, given the fact it's a 24-bit, unit, setting aside the error bit, you're going to have to reduce, because it kind of gets reduced to like 23 bits or something like that. But let's assume we ignore that for the moment. Well, 24 bits, is 16 million, levels of reading on this thing. Now, it's limited to 80 samples a second max, but your noise gets a little higher when you go to 80, 80 samples per second versus 10 samples per second. But that's up to you. It's optional how fast you want to read it. But you're probably going to have to use sample averaging, if you want to actually get some good information out of this. But but a DMM, if you're going to use it as like a multimeter kind of thing, most DMMs don't do more than 3 readings a second, unless you go with like an O1, like I, got on my test bench of, their XDM 1041 does like 60 readings per second, so you can actually data log with it at that rate, a little over 60 hertz. But at any rate, But if you're doing an average DMM project, you just want high precision. Okay, you can use something like this. But since it is differential, I mean, it does give you a plus or minus reading. So what that means is that instead of 16 megasample, you're really limited to, like, I mean 16, not mega sample, but I mean 16 million levels. You're really limited to about 8 million levels of reading. So um, yeah, and again, that's ignoring the noise bit. You got to take out. You're not going to get quite that resolution, but safely probably 4 million maybe. But that's 4 million on the plus side and 4 million on the bottom side. You could probably comfortably get. Again, I haven't really done any tests on these, but these are just some observations I made trying to do research on this. Eventually, I'm going to try this, but and get this stuff situated. But for right now, this is all theory. Um, but at any rate, that's still pretty high resolution. So if you applied 4 volts, for example, across some load resistor, if this could go up to 4 volts, and it can, I mean, again, as long as you put a resistor divider. So let's say we had a resistor divider, that will, put 4 volts across the thing, or allow you to put 4 volts across the thing that scales 4 volts down to 80 millivolts, with your voltage divider, and use channel B on it. All right, well, you could, after doing some math on the data you collect, yeah, you could, read down to, apply a 4 volt signal and read down to 1 microvolt. But again, there's probably going to be a lot of noise on that, so you're going to want to take multiple readings. But, at 80 samples a second, you can do quite a few readings, you're going to want to take quite a few readings and average them. So even still, it's probably not going to end up being that practical or that great. And the one thing that certainly you're going to have a problem with using, a chip anywhere, similar to this, is that, um, you're going to end up, hold on. Yeah, you're going to end up with so much precision, that how are you going to calibrate it? Okay, because I mean, frankly, in order to calibrate it, you're going to need some real expensive test equipment to do that. Like some Keithley, or Fluke, high-end desk, benchtop DMMs for it. Um, they're going to run you $2,000-3,000 or more. Even if you buy them used off eBay, it's going to pay out the nose for them. And if you had that, you wouldn't need one of these. So I mean, the point is, there's no real good way to calibrate it to that kind of precision. I mean, you're talking like a, upwards of, certainly 6 or 7 digit readout. So, it's really only so useful. I mean, yeah, you can use your, Fluke DMM or whatnot and calibrate it out to 4 or 5 digits. Well, 3 or 4 digits easily. But that's about the best you're going to do, assuming it's precise enough where you'll get good, reliable repeat readings. But you might be able to do that. The thing does have a thermal sensor in it, if you didn't notice, so you can actually take the take a a reading of the. At least I guess it has a thermometer, and I thought it did. But at any rate, you could take readings of it, of the temperature, and maybe make some kind of an adjustment so you can improve the precision, from day to day when you turn the thing on. You might get a slightly different reading, partly due to differences in temperature, and maybe partly just because the thing sucks, because, hey, it's, who knows who made it, for real, who knows if it's a knockoff of this particular chip or not, or if these guys even did that good of a job, I guess it's a pretty good data sheet they got here. It's more Western style as opposed to the normal data sheets you see out of semiconductors from China. Normally they're half in Chinese, and they're like 2 pages long, for complex chips, and they don't usually tell you much. This is, by that standard, a pretty good data sheet by comparison. But at any rate, the point is that it can be done, but it's not the greatest. But if you really want to explore these kind of things, there's a chip like this. Um, let's see, the that I got from Mauser actually a few years back. These aren't expensive. Okay, I didn't know I already had that up. Wait a minute. Hold on. Damn it. Uh, what what the fuck is this up for? Oh, damn! I hit the wrong button. Okay, yeah. If you're, I meant to hit pause on that. I clicked the wrong damn thing. So this is going to end up in the video. But yeah, if you wanted to look up this chip right here, I don't know if they still have them or not. Let me see. But you can, look up this chip here. I'm sure you can still buy them out there somewhere. Let's see. Let me see if they're still available at Mauser here. Wow. No, I guess they're not. Hold on. Alright, yeah, I guess I bought it from DigiKey, actually, because DigiKey has it, as you can see here, and they're not expensive. I mean, $1.73 in single unit quantities. They have a shitload of them in stock, and they're 3-hole, so that's what's great about them. I mean, I've had these, I've been sitting around for years, because I've been intending on doing a project with them. But what's nice about these things, if you pull up the data sheet, is that unlike the other HX711, this thing right here is not only 24-bit, but it allows you, it has a really versatile PGA. So what that means is there are like 7 different games you can set, from like 1 to ranging from 1 to like 128. So in other words, you can get a gain of 1, a gain of 2, a gain of 4, a gain of 8, a gain of 16, 32, 64, and 128. So in other words, you can basically eliminate the thing, and if you do, it can more or less go up to the supply rails. So again, you can practically get you can certainly get 4.5 volts out of it or something like that, full range. So, in other words, you can directly read, with a 4-volt applied voltage, even with no voltage divider, you can directly read, that 1 microvolt for the hypothetical 4-volt input, ignoring all other factors. So the good thing is this is like an American manufactured chip, I think. So, it's not going to be as dodgy as a lot of Chinese parts are, and so because of that, it may still be made in China, but it'll be supervised by, Americans. I don't know where it's manufactured, but again, I think this company is an American company, or at least a non-Chinese company, I think, but I could be wrong about that. But they don't really seem Chinese, because this is a real good, thorough data sheet. So I think this is a U.S. company or European or something. But anyway, the point is that this is likely going to be a better solution for you, and it ain't expensive. You got to buy it from DigiKey, so you'll have to pay like $5 in shipping, for whatever you order there. But the point is that well, maybe $8 or more. But just make sure you order enough stuff to justify it. But this is a lot better of a selection, but it basically has very similar properties, and it has similar, it's got the same 80 samples per second and all that. It's basically meant for a weight scale, but it's way more versatile than that thing you get off Amazon. So if you really want to do a meter, I would recommend this one. It'd be a lot better. Now, and again, it, like the other thing, is dual channel too, but when you set the gain for one channel, I think it applies to both channels. But the point is that at least you can adjust the gain of both channels. Just they have to be simultaneously adjusted, but they can adjust over 7 levels. And I don't know if there's like an Arduino library for it or anything, but it's probably not that difficult to use. It's going to be very similar to that other chip, with some modifications. So I'll bet you can modify the library for that other chip, to your needs if there's not one for this for Arduino. But at any rate, like I said, I do intend to, get into this, but just remember, that you're probably not going to be able to calibrate this or the other thing just because of the fact you're not going to have that precise as a standard. So unless you're rich. So, which again, you probably might not be that interested in this if you were, but not for a meter anyway. But the one thing you can do with it, and this is very important, is use it in a way that they're kind of using it for bridges. Because basically in bridges they're almost doing it, as a proportional comparison. So, in other words, they're not, usually directly measuring anything from it. They're putting it in a bridge, and measuring it in comparison to something else, right? So as long as you stick within that concept and use it for ratiomatic purposes, you can compare, for example, hypothetically, pretty accurately, one voltage to another, for example. So I'm not saying use it in a bridge. You can certainly do that, but I'm saying use it ratiomatically. So in other words, you can take channel A and measure one voltage, and again, they're differential inputs, so that means again, don't connect them to ground or anything generally, but have them as two independent little unrelated measurements if you can, that have their own power source, etc. Great example that is a voltmeter, because the voltmeter, when you stick the voltmeter on something, you got a load resistance, and again, usually a voltage divider or something like that, but your power actually comes from an external source that just make sure it's not ground reference to the circuit you're working on. So that way you can use the differential inputs. And I assume this has the same differential input. I know it does, in fact. It's going to have the same differential input concept that the HX711 does. But at any rate, if you use it for ratiatic proportions, like I said, you can take channel A and measure one voltage input, again, across the voltage divider, and then take channel B and use it, to measure a completely separate voltage, or it could be on the same circuit. I don't think that's a big deal. It's just the probes are differential, so you'll start getting a lot of noise and crap, a lot of times if you try to ground it to the unit itself. Remember, given the fact it's plus or minus scale, so I mean, for example, if you're trying to measure 4 volts, you really couldn't measure 4 volts, you would be measuring plus or minus 2 volts. So, you've got to bear that in mind. It may be able to range over 4 volts, but it's differential input. So, basically it cuts your scale in half. So, but that means you can measure, a positive voltage or a negative voltage with the same setup. So, if the voltage is negative, it'll give you a negative side reading. If it's positive, it'll give you a positive side reading. Now, it's not necessarily going to show up as a negative, but I mean, I'm sure it would if you used HX711, libraries or whatever. But really, it's going to be mid-range. In other words, it'll float, to that midpoint level. So if you put probes across a resistor, again, your full scale reading would be like plus 2 volts or minus 2 volts, for a total of a 4 volt range. But, that's why you can't just ground one of the leads. You're going to get into trouble doing that because you'll end up, you know, basically rel referencing one of your legs there, and you just can't do it. So you can't do it like you would in Arduino's ADC, which is not differential input. So the good news is you can measure voltages that swing both positively and negatively, but it does cut your scale in half, and it cuts your bit resolution in half, like I was kind of alluding to earlier, that you go from, instead of 16 million levels, you're really at 8 million levels, but 8 million levels positive and 8 million levels negative. So as a result, yeah, I mean, you'd probably, if you wanted to measure 4 volts, for example, you got to put a voltage divider on it still to take it from 4 positive volts down to 2 positive volts. So, but again, it could range over 4 volts. So if you had like an AC, really slow AC sine wave, for example, you could measure it, but it had to be slow because it's only 80 samples a second. But, the point is you could measure it, plus, a plus 2 volt peak, a 4 volt peak to peak sine wave, basically. You could measure that fine, as long as it's just no more than 2 volts peak, otherwise it'll start clipping. So, and you got to be careful on something like this, because again, its inputs are starting to approach the level of the supply rails. So if you're not careful, you can blow the thing out by applying too much voltage to it. So having a good healthy input impedance is always a good idea on any kind of meter if you can. 1 mega ohm or more, preferably 10, but it just depends on the precision of your resistors and stuff. But that's what's great about having something like this. You could theoretically actually build a high precision ohmmeter and compare 2 resistors with one another to a high precision. I mean, imagine being able to measure a 4 mega ohm resistor, for example, down to 1 ohm. So, or better of accuracy, So that's the kind of thing you need to think along the lines of. But again, how are you going to calibrate, such a high precision ohmmeter? You can't. I mean, I certainly don't have any ohmmeters that read out more than like 4 digits or so on my, in my possession. So, yeah, I mean, how do you do that? How do you calibrate it? Where do you buy a, 4.00, a 4 million ohm resistor that's more precise, down to the, the fraction of an ohm in precision. If you can buy those, that'll probably cost you more than a Keysight fucking, voltmeter, that would measure that kind of precision. So, I mean, at the end of the day, again, you got to think about using them as relative measurements. So if I wanted to compare 2 resistors, I could. In fact, I could compare a resistor of like 4 mega ohms to another resistor of 4 mega ohms, and use a high precision trimmer, to actually buffer out the difference so that they match precisely. Or better still, compare a 4 mega ohm resistor, down to to a high precision, and compare that with the same meter to see how it measures at 400 kilo ohms, so you get a 10-to-1 resistor ratio. Like, for example, you may want to use on an op amp to get a highly precise gain out of it. So if you wanted an exactly 10x op amp out of it, you could use something like this, because you don't care about the absolute value of the resistor, you care about the ratio of the 2 resistors. So there's a lot of different schemes you can go about that, and that's one of the things I really want to build this thing for. That's why I bought these chips several years ago, because I kind of wanted to do a project based on that concept, a ratiomatic meter, So again, because I have no way of calibrating it, but I can actually compare 2 resistors. And again, in a bridge, you're sort of doing that too. you know, but the difference is that you're dealing more directly with the actual values as opposed to a bridge. So, um, you know, we're really just looking for differences, you know. In this, you're actually dealing with the exact values, which is what you want. So, you know, you want to take a resistor before you soldered it into your board or whatever, you know, take a resistor and calibrate it, and then maybe build another little board, you know, that has a fixed resistor on it and a multi-turn high precision pot, you know, at least a 10-turn pot, you know, it makes up a big, you know, a small part of the resistance, but enough to where you could tune one resistor to either be equal to the other or equal to some ratio of the other. So, anyway, that's kind of the thing I'm looking at doing here. So anyway, you know, that covers that pretty long video, but you know, but it kind of gets the thing covered. Um, you know, but like I said, we'll see at a later date. You know, when I get around to getting my hands dirty with it. Well, cheers.